We've been solving linear systems of differential equations, first order ones, and in the case of a simple 2x2 system, then we can write out things in a very explicit form. So we'll have two coordinates, x and y, and we end up with a system of vector equations, basically. Now, there are methods by which to solve it, to get formulas for those answers, but another useful thing we did was talk about phase plane trajectories. So these were things like spirals and nodes, etc. This was a way to visualize the solution of a linear system. And in some way, it was independent of the actual answers we got. Now, computer systems can solve and plot these phase plane trajectories very easily. But we focused on talking about getting equations for these trajectories. So could we, for example, develop a Cartesian equation for something like a spiral or a center? Now, there were a lot of different ways that we went about this. So, for example, we could solve the system directly, get formulas for x and y. Both of those would be in terms of t. And then what we did in the past was eliminate the parameters. So we did some algebra to get rid of the t dependence and come up with some curves in the phase plane. So that's how we ended up with equations for centers, so circles, ellipses, spirals, star nodes, things of the sort. That was one option, and we've investigated that thoroughly for linear systems. Another option was something we did when we talked about nodes and saddles, so we could perform a qualitative analysis. So we weren't able to eliminate the parameter, but instead what we did was study how the eigenvectors and eigenfunctions behaved for large values of time and small values of time. So again, this is how we got the plots for nodes and saddles. A third option, though, is using something from calculus. Now, if we use something from calculus, we can remember that equations for x and y, they are parametric equations. And that means by the chain rule, we can solve for this y equals f of x directly. We would have to solve this particular first order differential equation. Now, from the system, we know what x of t and y of t are. So from the system, what we would end up getting would be cx plus dy over ax plus by. Now, this is, like I said, a first order differential equation, but because the x's and the y's appear in the denominator, this is a non-linear DE. And because it's a non-linear DE, all of the techniques we've been talking about so far don't apply. If we're going to go this route, we need to study properties of these first-order nonlinear DEs. And they do different things. They do strange things. We're going to take some time now to see some of the differences. We're going to compare and contrast. And we're going to compare this to our friend, the first order linear DE. So here's a first order linear DE. Now, you may or may not remember that a first order linear DE was something of this form. We had y prime was equal to negative p of t y plus some g of t here. This was the most general that a first order linear equation could be. At some initial time t naught, let's say we had some initial condition. There was a way to actually solve this. We could use integrating factors, and the integrating factor here would be simply the antiderivative of this term in front of the y. So let's call it r of t for now, and you can show, and we've done this many times, that the solution in this particular case is going to end up being dependent on the initial conditions over the integrating factor plus this integral from some t naught to t integrating factor g of t, or I should say g of tau d tau. Because we have this formula, we have all the information we need about the solution. And this leads us to a theorem. And the theorem that we get is probably something we've taken for granted already. Let's say that this function p and this function g are commonly continuous on some interval a and b, and let's take that initial value to be somewhere in that interval. So on this interval, which we can identify ahead of time, we know that the two functions are nice and well behaved. So then the linear first order initial value problem, this one that we've got right here, we'll put a little star by it. This initial value problem has a unique solution for all t values that live in there. Now that is a very strong statement. It's a very strong theorem. It tells us, number one, that tells us that we have an answer, number one. Number two, it tells us it's unique. And number three, it tells us exactly where it's going to live. So this is really nice. Linear DEs are very nice. We like them. We get existence, we get uniqueness, and we have all of this for the entire interval. And what's even nicer, we can see before solving, where the solution exists and how it depends on the initial conditions. That's really nice. So you know everything about linear DEs. They're great. Well, now it's time for us to contrast this with a non-linear DE. So here is, in general, a first-order non-linear DE. And they kind of look like this. Let's say we've got our first derivative, y prime of t. It's equal to some function of t and y. And again, we'll always have an initial condition. Now, this function right here is a non-linear function. We don't know what it is. So, for example, it could be any non-linear function of y. It could be e to the power of t times y. It could be cosine t cosine times t times cosine of y, etc., etc., etc. It could be anything. And because of this, there is no general theorem like we have above on existence or on uniqueness, and probably more in the line of what you're thinking, there is no general solution formula. So that's probably upsetting, right? You just want to memorize the formula and go from there. And it can have very strange behavior. Now, I should say there's no general theorem, but there is a theorem that's going to tell us a little bit something here. There is a theorem here, something called Picard's theorem. Now, it's a little bit technical, and it gives us something like this. If we have this first order differential equation, and it's a nonlinear one, so let's say we've got this y prime equals f of t and y, and we've got our initial condition. So the statement of the theorem kind of goes like this. If the function is continuous on some, we call it an open rectangle, and I'll try to draw you a picture. Remember that here we are in the t y plane, if t goes from a to b and y goes from alpha to beta, they can draw or trace out some open rectangle. So everything in here, and we'll call this rectangle R. So there's the rectangle R. And the partial derivative of that right-hand side with respect to y is continuous on R near the point right here. Let's call this point t0 and y0. So if these conditions are true, then there exists some interval. And that interval we're going to call CD, and we don't know what it is. It lives somewhere between A and B. So in terms of the picture, let's say C and D are somewhere here. So this interval exists where the initial value problem has a unique solution. So that's another theorem. Now, proving this requires more in-depth analysis, but that's not really the point of what we're doing here. We're just trying to see what we can say. Now, you might think that, oh, this is a mathematical statement and things are great, but this theorem isn't of much worth. And why is that? Okay, the problem here is it doesn't tell us what this interval CD is. We don't know where it is. We don't know how large it is. And if we violate any of the conditions, the theorem doesn't hold. Unless the conditions hold, obviously. And then the other thing is the DE can still do strange things. And I'm going to try to illustrate this with a couple of examples. Linear first-order equations, very nice, very strong statements about existence and uniqueness of the answer. Nonlinear equations, much more difficult, much more vague. It's not as precise about what we can know ahead of time. The other problem is we may not be able to actually solve them. All of the tricks we've been working on and using don't apply anymore. So this seems like a lot of bad news. Let's take a look. Let's see what we can figure out. Here is a nice looking, anyways, nonlinear differential equation. This thing right here is the function of t and y. This is our right-hand side. It turns out just to be an explicit function of y. Now, partial derivatives work very similarly to ordinary derivatives. You pretend that one of all the other variables are constant and you differentiate with respect to the one you've been given. Here, that's very straightforward. We're just going to get a 2y. Now, each of these functions is continuous on all real numbers for t and all real numbers for y. Looks great. Everything looks really, really nice. All these functions look great. We must be able to solve this very easily and get a nice, wonderful answer, right? Now, we'll learn how to get a formula for it in another place, but here's the idea. We can show that the solution looks like this. The solution is going to be given by a formula, which we think is great. And the formula kind of looks like this. This is strange. There are some problems. Right here, the solution, we'll say, it blows up at this time equals y0. The solution doesn't exist. If I were to take a look and plot this function for various values of y0, what I'm going to find is that there's a big vertical asymptote. Holy smokes, I couldn't see that. I can't determine this from the DE or the initial conditions ahead of time. I have to actually solve the DE to see where this is. The other thing is the solution doesn't exist for all t values. Right? I didn't know that there's nothing over here. The solution doesn't exist past a certain time. I couldn't tell from looking at the problem that that kind of thing was going to happen. That's very different than a linear equation. When you have a linear equation, you look at the coefficients and you can see, oh, there's going to be a problem there, or the function's not continuous, so I shouldn't expect the answer to be continuous. Non-linear equations are weird. We don't get existence everywhere we want it. Now, other nonlinear equations can do other strange things. So for example, let's take this one. This is nonlinear because we have a square root and an absolute value. So this is our function. And we should note this function doesn't satisfy the conditions of Picard. So that means we shouldn't expect the theorem to hold. So we can't really read into what the theorem is going to tell us here. The point of showing you this example is the following. You should be able to easily see that if I take y equals 0, I'll satisfy the initial conditions and the differential equation. So I'll satisfy the whole thing. Y equals 0 will work. Now again, without getting into it, you can show that this function also satisfies the differential equation. So this solves the initial value problem. Well, what's going on here? If I take a look at this and I plot y versus t, remember that y equals 0 is an answer. So this horizontal line will solve the DE. That's always an answer. And then I've got this piecewise parabola going on here. So this piecewise parabola says, okay, you'll have one branch looking like this and another branch looking like this. Well, here's something really unique that we did not see before. We have non-unique solutions. There are two answers at t equals 0. That didn't happen for linear equations. This is different than a linear DE. In a linear DE, we always get unique solutions. That means in a linear DE, you can't have solutions crossing. That's not possible. But in a nonlinear equation, you can. Solutions can cross. These two simple examples are meant to show you, not to dishearten you, but to show you that we're dealing with a very different animal now. And we can solve these nonlinear DEs in some special limited cases. So what we're going to do is set ourselves about that path. And we have to remember that we aren't going to be as successful as we were with linear equations. Nonetheless, it's important to try to exploit everything we can for nonlinear equations and then see where to go after that.